Chapter 8. Gene Therapy and CRISPR, the Cure for Disease. Gene therapy and CRISPR are upending the way we treat and cure disease. The power to control our species' genetic future is awesome and terrifying. Deciding how to handle it may be the biggest challenge we have ever faced. I believe that we are up to the task. Jennifer Doudna, Ph.D., inventor of CRISPR and 2020 Nobel laureate in chemistry. I'm sure many of you have heard of the miracles of gene therapy. Some of you might even be confused by it. But if there's one thing I want you to understand from this chapter, it's that gene therapy is a chance for us to literally eliminate disease, not treat it, but cure it completely. In this chapter, we'll show you that gene therapy is not 20 years in the future. We'll show you how it's being used today and what it can be used for in the near future to make a difference in your life or the life of someone you care about. In this chapter, you'll see some stunning examples of the many ways this ability to harness gene therapy and gene editing is being used to create more effective treatments. For example, can you imagine that you could cure your child's congenital blindness with the mere injection of a CRISPR treatment into the back of their eye? As you'll discover, this is happening today. Imagine using gene therapy to reprogram damaged heart cells, scars, and convert them into healthy, beating heart cells. You'll learn how scientists using CRISPR restored the eyesight of a teen crooner on America's Got Talent, helping him to overcome his inherited genetic disorder. You'll hear about a company that's applying CRISPR gene editing technology to relieve Alzheimer's symptoms such as anxiety and depression, and about a researcher who's using CRISPR to block the aging process. You'll learn about what scientists are calling the jackpot gene, the gene that dramatically lowers your risk of Alzheimer's and can significantly enhance your longevity. But first, let me tell you a quick story that my co-author Peter and his writing partner Stephen Kotler covered in their recent best-selling book, The Future is Faster Than You Think. The story is a powerful recounting of the miracle of gene therapy and its ability to cure what was previously a death sentence. The 1970s were good for John Travolta. While the actor had broken through with a supporting role in 1972, he captured the public's attention in his starring turn in the 1975 TV show Welcome Back, Kotter. But it was playing the protagonist in the 4-time Emmy Award-winning made-for-TV movie The Boy in the Plastic Bubble that cemented him as a real star in 1976. The movie was based on the life of David Vetter, a boy from Texas who suffered from X-linked severe combined immunodeficiency, a genetic disease that destroys the immune system. Living with this condition requires living inside a bubble, a self-contained atmosphere that protects against any and all germs. Everything that passes into the bubble, water, food, clothing, has to first be sterilized. For patients with the disease, simply breathing normal air can be fatal. About 4 years before Travolta took his turn in the bubble, an article in Science argued that a new form of treatment might hold promise for patients with severe combined immunodeficiency and other genetic diseases. Known as gene therapy, the idea was unusual, yet useful. Genetic diseases are caused by mutations in the DNA, your genome, your code for life. So the solution was to find a way to replace that bad DNA with good DNA, or, in computer terms, debug the system. But how to get that good DNA into place? That's where the viruses came into play. These microscopic parasites thrive by attaching themselves to cells. Once there, they inject their own genetic material into the nucleus, causing the host to replicate the virus's DNA, like a hijacked assembly line. Gene therapy piggybacks on this process, stripping out the disease-causing portion of a virus's code and replacing it with good DNA. Once the virus injects the good DNA into the host cell, first the symptoms of the disease disappear, then the disease itself is cured. While the promise of gene therapy is tremendous, the science was not easy. It took almost 2 decades for the first treatments to arrive, which is when the trouble started. In 1999, an 18-year-old boy named Jesse Gelsinger, with a rare metabolic disorder, took part in a gene therapy drug trial at the University of Pennsylvania. Gelsinger's condition wasn't fatal. The combination of an extremely restrictive diet and 32 pills a day kept symptoms under control. But the trial had the potential to cure him completely, so he signed up. 4 days after receiving the initial injection, Gelsinger wasn't cured. He was dead. The first recorded death from gene therapy. More mishaps occurred. Not long after, in a gene therapy trial in France aimed at treating bubble boy disease, 2 out of the 10 children involved developed cancer. Immediately, the FDA suspended all gene therapy trials until further notice. The dot-com crash in 2001 was the killing blow, as money from the exploding web had been fueling gene therapy startups. This was the dank pit of the deceptive phase, from which many were convinced there would be no escape. But escape did come, in the form of more science. Even though gene therapy faded from sight, research continued, and continued. Then, on April 18, 2019, it burst back into view with a staggering announcement. Bubble boy disease had been cured. 10 babies born with the condition, born technically without immune systems, had been treated. It wasn't that their symptoms were better. It wasn't that their condition was manageable. It was that they were cured. Before treatment, they didn't have immune systems. After treatment, they did. The disease was gone. The missing DNA, the missing genes, had been craftily reinserted into the bone marrow of those 10 babies. Biotechnology is about using biology as technology. It's turning the fundamental components of life, our genes, proteins, cells, into tools for shaping and improving life. In a very real sense, this story starts with the human body, which is a collection of 30 trillion cells, the function of which determines our health. Each of these cells contains 3.2 billion letters from your mother and 3.2 billion letters from your father. This is your DNA, your genome, the software that codes for you. It's your hair color, eye color, height, a significant chunk of your personality, propensity to disease, lifespan, and so forth. Until recently, it's been difficult to read those letters and even tougher to understand what they do. The Human Genome Project is a research initiative that began in 1990 with the goal of sequencing or identifying all of the chemical units that make up the genetic blueprint required to build a human being. It took 13 years to complete and is one of humankind's greatest achievements. At the time, the goal seemed nearly impossible, and some skeptics predicted that the costs would run wild, soaring perhaps uncontrollably to hundreds of billions of dollars. But as we all know from Moore's law, technological progress is like an unstoppable force of nature. It's an accepted truth in Silicon Valley that technology tends to grow twice as powerful every 18 months, while the price halves. One of the few people who foresaw with certainty that the genomic sequence could be achieved was my dear friend Ray Kurzweil, one of the greatest engineers and inventors of this century. Knowing how technology compounds in power and drops in cost, Ray not only recognized that the entire genome could be sequenced in under 13 years, but even predicted the timeline and the cost, estimating it would cost $2.7 billion. Yet after 7.5 years of intense scientific research, the international team was able to sequence only 1% of the human genome. Skeptics pointed to failure and said that at that rate it was going to take 700 years to complete. And yet, Ray Kurzweil knew the team was exactly on track. How? Because 1% is only 7 doublings from 100%, and it had been doubling every year. Sure enough, less than 6 years later, we miraculously achieved this feat of humanity on budget and on time. We don't think in these exponential terms, and that exponential growth has continued since the end of the Genome Project, said Kurzweil. Since then, the price has plummeted, outpacing Moore's law by a factor of 3. Today, what cost $2.7 billion and took 13 years can be done in a few days and costs less than $1,000. That's such a staggering drop in price that it's a bit like being able to buy a Tesla Model X for a nickel. In fact, a few years from now, companies like Illumina are promising to do the same in an hour and for $100. Why does cheaper, faster genomic sequencing matter? Because it gives us a map of how cells function so we can design better interventions. It's a healthcare game changer. Put differently, there are a few main ways to fix a cell. Gene therapy replaces defective or missing DNA inside a cell. Gene editing techniques like CRISPR allow you to repair the DNA inside the cell, and stem cell therapies replace that cell entirely. Thanks to our increasingly accurate maps, all of these interventions are now hitting the market. The biggest news of the last few years is CRISPR-Cas9, which has become our leading weapon in the fight against genetic diseases. The discovery and application of this technology earned Jennifer Doudna and Emmanuelle Charpentier the 2020 Nobel Prize in Chemistry. This year's prize is about rewriting the code of life, declared Göran Hansson, the Secretary General of the Royal Swedish Academy of Sciences, when he made the announcement of their Nobel Prize. Considering CRISPR's wide-ranging potential, it was practically an understatement. Technically, it's an engineering tool that allows us to target precise locations in the gene code and then edit that DNA. Want to remove the string of DNA that produces muscular dystrophy? Simple. Just target that spot in the genome, unleash CRISPR-Cas9, and snip, 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 problem solved. One way to think of it is as the genetic equivalent of a trusty word processing program. CRISPR allows its users to snip a stretch of DNA and then either disable the affected sequence or replace it with a new one. At this point, you may be asking the same question I did. What is the exact difference between CRISPR gene editing and gene therapy? They sound very similar, don't they? Here's the key point to distinguish them. While CRISPR gene editing fixes a typo in the existing genome, leaving the original gene with its typo corrected, by contrast, gene therapy injects a completely new copy of an entire gene into the cell's nucleus. In some diseases, where the correct gene was missing altogether, gene therapy will add what wasn't there. In other cases, where there is an incorrect copy, gene therapy can add a correct copy, which helps offset the disease. Another key point is that CRISPR uses an editing protein discovered in bacteria called CRISPR-Cas9. By the way, there are many different Cas proteins. Cas9 is just the most famous. To find the errant DNA and make the edit. Gene therapy, on the other hand, uses a specially modified virus as a vector to deliver the new, healthy gene into the target cells. The viruses act like biological delivery vans, whisking a correct copy of the gene into the nuclei of the malfunctioning cells. This may sound complex, but gene therapy's allure can be explained very simply. It's a one-time treatment that cures the disease instead of a therapy that must be repeated for the rest of your life. A quick fix instead of a lifetime of popping pills or enduring injections. A cure instead of a patch. A patch can smooth things over, but a cure? A cure can completely reshape a person's entire life. I don't want these stories to merely astonish you. I want them to give you new hope. And you know what the best part is? Genetic interventions like these are not far off pie-in-the-sky possibilities. In fact, more than 2,500 gene therapy clinical trials have been approved, are in progress, or have already been completed as we speak. Over the next few years, these transformative genomic technologies could change or save your life or the lives of the people you love. Curing blindness with gene therapy. I once was lost, but now I am found, was blind, but now I see. Amazing Grace. Dr. Peter Marks is the director of the Center for Biologics Evaluation and Research at the FDA. It's a hugely important job overseeing the branch of the agency responsible for approving new medications, including gene therapies and vaccines for threats like COVID-19. By late 2020, only 2 gene therapies had secured FDA approval. But more than 1,000 active investigational drug applications for gene therapies were pending at the agency, an indication that this technology has reached a major tipping point. Soon there will be gene therapies for scores of diseases. Even during COVID-19 times in the first half of 2020, we were on track to receive as many or more gene therapy applications as we received in 2019, says Marks. Gene therapy is the wave of the future. Ultimately, Marks expects the gene therapy revolution to encompass all kinds of illnesses. For example, Alzheimer's disease, various cancers, even high cholesterol. But for now, rare diseases are the prime target. When we talk about rare diseases, you might assume that these are obscure disorders affecting a handful of people. But would you care to guess how many people have a rare disease? Answer: 7,000 rare diseases affect up to 30 million Americans. That's almost 1 in 10 Americans impacted by a rare disease. The majority of these diseases have a genetic component. What's more, fewer than 10% have an FDA-approved treatment. That combination, lots of sick people, not a lot of good treatment options, means that the rare disease category is ripe for groundbreaking interventions involving gene therapy and gene editing. Zolgensma, the second gene therapy approved in the U.S., essentially cures spinal muscular atrophy. The first, Luxturna, is turning night into day, restoring sight to people with hereditary blindness. To explain why I'm so excited about these medical advances, let me tell you a story. In 2017, when Christian Guardino was 16, he appeared on America's Got Talent. He brought the house down with a soulful rendition of Ed Sheeran's song, Let It Rain. The performance left Simon Cowell speechless, which is quite a feat. Another judge, Howie Mandel, was so blown away that he awarded the Golden Buzzer to Guardino, automatically sending him to the next round. Guardino couldn't believe his eyes as he gazed down from the stage at the celebrity judges and the ecstatic audience. He recalls, "Because I'd been visually impaired for so long, to be able to see those 4 judges sitting there watching my performance was amazing." Guardino's mom loves to tell the tale of how she discovered that her son was musically talented. One day when he was a few months old, she sang scales to him while he splashed in the tub. He sang them back in perfect pitch, prompting her to call her mother and ask, "Is this normal?" But at around the same time, the family was hit with distressing news. Guardino was diagnosed with Leber congenital amaurosis, LCA, a rare eye disorder caused by inherited genetic mutations. In the years after his diagnosis, he had a number of painful collisions. One time he slammed into a mailbox while playing football. Another time he needed stitches after crashing into the kitchen table. He simply hadn't seen them. Over time, his vision darkened, shadows lengthened, and he turned to music as a coping mechanism. He might not be able to see, but at least he could sing. Then in 2012, Guardino learned about some cutting-edge researchers who were developing a new gene therapy. He joined a clinical trial and received 1 injection of Luxturna in each eye, 1 week apart. They put a gene in a safe virus, and that virus helps the gene find its missing place in me, says Guardino, providing a simple and accurate description of how gene therapy works. That was in June 2013. The day after the first injection, he removed his eye patch and glanced at the floor. To his amazement, he saw diamond shapes on the carpet that he'd previously thought had no pattern. It was pretty crazy, he recalls. Since then, he's seen countless incredible sights: the moon, the stars, fireworks blazing across the night sky. It worked, says Guardino. Boy, did it work. After he was awarded the Golden Buzzer on America's Got Talent, Guardino was heading out when Simon Cowell stopped him. Cowell had just heard Guardino's backstory from a producer. "Wow," said Cowell. "You didn't let your disability stop you. It doesn't define who you are." For Guardino, that exchange was one of the highlights of the whole unforgettable experience. "I always thought LCA would define me, but that night it didn't. Simon heard my voice, and he liked me without even knowing my story. It made me feel incredible about myself. In the end, Guardino was knocked out in the semifinals, but his appearances on America's Got Talent led him to release several singles and perform all over the country. He still gets pre-show jitters, but nothing that approaches the pressure he felt before his most important performance to date, testifying before an FDA advisory committee about the need for Luxturna to be approved. He recalls telling the panel of scientists, "It's either this or we go blind." In 2017, the FDA voted unanimously to approve Luxturna, making it the first gene therapy to be given the green light. The hero who found a cure for blindness. There was no roadmap. We were on our own. Dr. Kathryn Hai, former president of Spark Therapeutics. One person who joined Guardino on that historic day was a pioneering scientist named Dr. Kathryn Hai, who was largely responsible for Guardino's ability to see the diamond-patterned carpet and the moon in the sky. "Science will be changed forever because of what Kathy did," says Guardino, his voice thick with emotion. "She changed my life." For Dr. Hai, it's a lifelong calling to help people achieve their destiny. People born with serious genetic defects don't have the same chance that someone else does, she says. If we can fix that and level the playing field, they have the chance to be who they were meant to be. Hai's scientific ambitions began early. When she was 10, Santa brought her a chemistry set with instructions for how to carry out more than 100 experiments. She spent many hours mixing and tinkering alongside her father, who had big dreams for his daughter. This was the early 1960s, when it wasn't common for a woman to enter the sciences, let alone make a name for herself. Hai's father wanted her to attend MIT, become an aeronautical engineer, and work for NASA. She chose a different path to scientific glory, majoring in chemistry at Harvard, and then enrolling in medical school at the University of North Carolina at Chapel Hill, UNC. After a hematology fellowship at Yale, Dr. Hai returned to UNC and worked on understanding the molecular basis of hemophilia. UNC had a hemophilia dog colony, and she tried using gene therapy to correct the canine's gene malfunction. Those early efforts failed, but she continued to focus on hemophilia at Children's Hospital of Philadelphia, CHOP. In 1999, Dr. Hai published a landmark paper showing that her team had succeeded in curing hemophilia in a dog model using gene therapy that relied on vectors, viruses that carry the corrected gene to the spot in the genome that's malfunctioning. These viruses had been manufactured by a California biotech company that folded in the 1990s, along with almost every other gene therapy startup. Back then, the science seemed promising, but the timing was all wrong. The technology sounded like science fiction, remotely plausible but a bit unlikely. Does Dr. Hai sound like a person who was ready to call it quits? No way. She appealed to the CEO of CHOP, one of the nation's most prestigious children's hospitals, to set up vector production so she could continue her research. "I figured he'd say no because no one believed that gene therapy would work," says Hai. "But to my great and undying surprise, he said yes, with one condition." He told her, "You can't spend all this money only on hemophilia. You also have to work on other diseases that affect children." As luck would have it, Dr. Hai was friends with a scientist named Dr. Jean Bennett, who also worked on dogs. Dr. Bennett, who was researching a rare form of inherited blindness, had data indicating that a particular gene therapy corrected the dog's vision. This raised an intriguing question. Could her research be developed so it would help humans with certain forms of inherited blindness? In 2005, Hai and Bennett teamed up. In 2007, they launched a clinical trial. In 2012, they moved to Phase 3 testing. In 2013, they formed Spark Therapeutics to bring this therapy, a gene that encodes an enzyme found only in the cells in the back of the eye, to market. Dr. Hai became Spark's somewhat reluctant president and head of R&D, leaving the best job in the world in academia to turn this moonshot dream into a reality. "I was able to recruit people I couldn't have gotten had I not been willing to go in myself," she says. I'd spent much of my academic career trying to move gene therapy forward, and this was the point when I had to say, if this is what it takes, that's what I'm going to do. It's been a long and winding road since those early days of working on dogs with hemophilia, but Dr. Hai's persistence has paid off spectacularly. The prize at the end of the road was Luxturna, a gene therapy product that's now used to treat patients with an inherited retinal disease caused by mutations in both copies of their RPE65 gene. When that gene doesn't work properly, the results can range from progressive vision loss to complete blindness. Some babies are diagnosed when their parents notice that they're not tracking objects with their eyes. Others are diagnosed later in childhood. By age 12, most kids with this disease need to be placed in Braille classrooms. Can you imagine being a parent in that situation and discovering that a single injection into each of your kids' eyes could cure your child's blindness? It's almost biblical in nature. After these injections, the cells in the retina of each eye are able to produce the RPE65 protein, which enables the visual cycle to work properly. I ask you, what could be more miraculous? Dr. Hai, one of the great pioneers of gene therapy, expects more approvals to come with each passing year. At Spark, our saying was, we don't follow footsteps, we create the path. There was no roadmap, we were on our own, she says. What's that saying? The early bird gets the worm, but the second mouse gets the cheese? Every product builds on the product before. There has never been a greater time to be alive. Doug Ingram, CEO of Sarepta Therapeutics, a leader in gene therapy for rare disease, says it best. The time is now. We have an opportunity that historically has not been possible over the arc of human history, to use the tools of gene therapy and eventually gene editing to create a better life at minimum and perhaps completely transform and save lives. We're trying to lead a revolution, dragging tomorrow into today, bringing gene therapy to patients who need it now. Here's the bottom line. If you are or someone in your family is one of the 30 million Americans living with a rare genetic disease, there has never been a better time to have hope that a treatment, or even better a cure, lies around the corner. Thanks to gene editing and gene therapy, diseases that have historically had no available treatments are now on the cusp of breakthroughs. Remember, more than 2,500 gene therapy clinical trials have been approved, are in progress, or have already been completed. Don't resign yourself to thinking there's no solution. Connect with the special interest group associated with your disease and ask if they are working on clinical trials using CRISPR or gene therapy to relieve your symptoms. Before you know it, we will see the day when every genetic disease can be treated. How gene therapy can fix a broken heart. Our cells retain their youthful digital information even when we are old. To become young again, we just need to find some polish to remove the scratches. David Sinclair, Ph.D., Lifespan, Why We Age and Why We Don't Have to. I want to highlight the brilliant work of Dr. Deepak Srivastava, a cardiologist who is president of the Gladstone Institutes, a biomedical research organization at the forefront of the revolution in regenerative medicine. Srivastava, a member of our Life Force Advisory Board, shared information about how he's using gene therapy to repair heart damage. As Srivastava explained, the heart is chock full of cells that we call fibroblasts that normally send important signals to support the muscle, and they also make scar tissue when the heart is injured. These fibroblast cells produce excess collagen when activated under stress, and this has a negative impact. But what if you could control the fate of those fibroblast cells, reprogramming them so they could perform an entirely different function within the heart? Incredibly, that's what we've been able to do, says Srivastava. Here's how it works. In experiments with mice, Srivastava used gene therapy to deliver a combination of genes into the fibroblast cells in the heart after the mice suffered a heart attack. One injection of these genes was sufficient to change the fate of the fibroblast cells, turning them into beating heart cells. Peter refers to this approach as nothing less than cellular alchemy. That's right. Shrivastava was able to create brand new muscle in a failing heart by convincing fibroblast cells already in the heart to change jobs. We're reprogramming a cell's fate, he says. As I'm sure you can see, the implications are mind-bending. Now that scientists have figured out how to control the fate of cells, it's not hard to imagine using the same approach to repair tissue damage caused by everything from brain disease to liver disease. For Shrivastava, this research took on new meaning when his father recently died after many years of living with a damaged heart that impaired him severely. We do everything with a great sense of urgency because there are people out there who are waiting and dying. I think about it every day. How we need to do everything we can to accelerate. We weren't fast enough for my father. But Shrivastava hopes to be fast enough for folks like you and me, our parents, and our kids. The good news is that Gladstone Institute keeps spinning out new companies to develop these regenerative technologies, so they'll be available to us in the years to come. One of these biopharmaceutical startups, Tenaya Therapeutics, is working on curative therapies for heart disease, the world's leading cause of death. Among other things, Tenaya, which went public in the summer of 2021, is trying to reprogram fibroblasts as a way to replace lost heart cells and restore cardiac function after patients have had heart attacks. The miracle of CRISPR, editing the errors in our DNA. The more we know, the more we realize there is to know. Jennifer Doudna, Ph.D., inventor of CRISPR, 2020 Nobel laureate in chemistry. That goal of redefining the human race is already well underway thanks to Jennifer Doudna, Emmanuel Charpentier, and their discovery of CRISPR-Cas9, the gene editing mechanism that resulted in them being crowned Nobel laureates in 2020. Remember, while gene therapy involves inserting a new, missing, or corrected gene into your cells, CRISPR gene editing involves editing an existing gene, repairing the incorrect letter that is or letters that are causing a genetic disease. In other words, this tool is used to edit the genome that determines so much of who you are. In a 2015 TED Talk, Doudna explained that it's analogous to the way that we use a word processing program to fix a typo in a document. But in this case, we're talking about changing the code of your life. Doudna grew up in Hawaii, where the natural beauty of the islands inspired her interest in biology. Her father, a professor of American literature, loved to read about science and gave his daughter a seminal book about the discovery of DNA's double helix structure when she was in 6th grade. Inspired to pursue a career in science at Pomona College, she had second thoughts while enrolled in general chemistry and wondered if she should switch gears and major in French. We have her French teacher to thank for encouraging Doudna to stay the course and eventually help develop CRISPR, which has revolutionized the field of genetics. Not content with pioneering the field of gene editing, Doudna has helped to advance it further by co-founding Mammoth Biosciences, a company dedicated to unlocking the potential of the next generation of the technology by discovering new proteins. You might call it CRISPR 2.0. You know what's really cool about these new versions of CRISPR? They are not being engineered in a lab. They're being discovered in nature. For non-scientists like me, this whole process can seem a little intimidating, but the bottom line is simple. The fact that more of these novel CRISPR-associated proteins are being identified is wonderful because it means that more options now exist to perform exquisitely targeted gene editing and to make multiple edits at the same time. That's great news for precision medicine. The future is limitless because bacteria and their proteins are everywhere. In fact, there's already another even more precise version of CRISPR-Cas9 called prime editing that sidesteps some of its less desirable outcomes. In principle, the technique called prime editing could correct an estimated 89% genetic variance known to be associated with human diseases, declares the Journal of the American Medical Association. That's quite a statement, isn't it? Every time you turn around, there's another huge leap forward. In the meantime, as Mammoth continues to amass a portfolio of different versions of CRISPR, the firm is mulling where to deploy its powerful tools and how to enhance them. They've now been able to inject CRISPR straight into the bloodstream and direct it to the liver to cure amyloidosis, a disease that causes pain and fatigue and disrupts the nervous system. But these brilliant scientists are still striving for more. Next, they might optimize cell lines to help bring drugs to market faster. Some are beginning to target diseases like cystic fibrosis or sickle cell anemia that are caused by an error in a single gene. It's amazing to think that these naturally occurring tools can be deployed in so many life-saving ways. We're unlocking the potential of CRISPR to tackle all sorts of diagnostics and therapeutics by unlocking new proteins, says Mammoth's CEO and co-founder Trevor Martin. We could sit down and try to engineer this from scratch, but instead we're saying, let's tap billions of years of evolution and leverage the diversity of life. As it turns out, CRISPR not only edits the genome, but can be used to detect DNA too. Mammoth Biosciences is deploying CRISPR to be a DNA detective to sniff out DNA snippets that might signal viral infections, cancer, or defective genes. In 2018, it was first used to detect 2 strains of human papillomavirus, HPV, and now it has already been expanded for use in detecting bacterial infections, cancer, antibiotic resistance, and other viral infections such as COVID-19. A separate test using a different version of CRISPR is being used to rapidly diagnose Zika and dengue virus. Not only that, but these tests are rapid, only taking 20 minutes. I want you to understand the potential of this technology. CRISPR was a scientific breakthrough for gene editing, and now it's going to revolutionize diagnostic testing. The world will soon see rapid, reliable diagnostic tests that are easy to use from the comforts of your own home. The jackpot gene. Now, I need you to pay close attention here for 1 minute because I'm about to explain a so-called jackpot gene that dramatically lowers your risk of Alzheimer's, and it's a tiny bit technical. It's well known that the 10 to 15% of people who carry the ApoE4 allele, or version of the ApoE gene, are at much greater risk of developing Alzheimer's. But you know what's cool? The ApoE2 allele, which is the rarest version of the gene, carried by only 7% of the population, is associated with a much lower risk of Alzheimer's-related decline, not to mention enhanced longevity. Sign me up for that version. At the Buck Institute for Aging in Marin County, California, Dr. Lisa Ellerby is using CRISPR to investigate the mysterious neuroprotective role that ApoE2 plays in aging and disease. I like to call it the jackpot gene because if you're lucky enough to have it, you've hit the genetic jackpot and have more protection than people without it. Did you know that women are at greater risk of developing Alzheimer's than men? Dr. Ellerby hopes her research will shed light on why it's more common for women to be diagnosed with the disease. She's also using gene therapy to deliver the ApoE2 gene into aged mice to see if its expression or any related treatment increases health span. If we can figure out a way to translate this to humans, allowing us to access the magical benefits of this jackpot gene, it would be a true miracle. As we've seen in this chapter, gene therapy and CRISPR are extraordinary tools for curing disease. But one of our advisors, George Church, a founding father of genomics, sees gene therapy as a tool for curing the one disease that affects everyone everywhere: aging. The idea with gene therapy was that you have someone with a rare genetic disease that's missing a particular protein and you just put it back in. But the problem is, your body recognizes that protein as being foreign and there's a chance you'll reject it. By contrast, his strategy of using gene therapy to reverse aging involves putting in proteins that are already there. They've just diminished over time. We're just turning up the knob on genes that are already in your genome. That only begins to convey the boldness of Dr. Church's ambition. What's his ultimate goal? A preventative elixir to reverse aging. I recently spoke with him over Zoom about this topic and wrapped up our conversation by saying, "Thank you for your time and thank you for your life's work." You know how he responded? He said, "Tony, you can thank me when you're 150. Let's turn now to hear the heroic story of the team that's paving the way for curing disease using a pathway to power. Let's learn about the wondrous WNT pathway.